Dear students, welcome back to the second semester BSc Physics class. In this session, we shall discuss about TS diagram, concept of absolute zero and the third law of thermodynamics. Usually, we draw a PV diagram for the working of a Carnot engine. From the PV diagram, we get the information about the working of Carnot engine in one cycle. The plot PV diagram, which is a graph of pressure versus volume changes of the working of a Carnot engine. From this PV diagram, we can calculate the efficiency of the Carnot engine as well. In a similar way, one cycle of Carnot engine can be represented by plotting temperature versus entropy change. This is similar to the PV diagram, but it is very advantageous in measuring the entropy of the system by using the TS diagram. The thermodynamic changes in the state of a substance can be represented by plotting entropy S along horizontal axis and temperature T along perpendicular axis. Such a diagram is called TS diagram for the substance. In the figure, you can observe the TS diagram, which comprises of two isothermal processes and two adiabatic processes. These two isothermal and adiabatic processes are represented along the four curves AB, BC, CD and DA. A Carnot reversible cycle is shown on the PV diagram. We can observe the picture. It comprises of two isothermals corresponding to isothermal expansion represented by the curve AB and isothermal compression represented by the curve CD. These two isothermals are drawn at two different temperatures, T1 and T2 respectively, where T1 is the temperature of the source and T2 is the temperature of the sink of a Carnot engine. Here you can observe the TS diagram shown in the figure 2. Here also there are isothermal curves which are called as isotherms, and there are two isotherms represented by the two straight lines. You can observe two straight lines are drawn for two isotherms AB and CD. These are parallel to each other and they are parallel to x-axis. X-axis represents the entropy and it is named as S-axis also. And there are two adiabatic curves represented by BC and DA. These two are also two straight lines. These two curves are all called isentropes. The isentropes are parallel to the temperature axis. Thus, the resulting TS diagram is a rectangle ABCD. Now, let us look into the Carnot cycle on TS diagram. A Carnot cycle comprises of isothermal operation as well as adiabatic operation. In an isothermal operation, the temperature remains constant. Isothermal means, iso means constant, thermal means temperature. You know it very well during the explanation of the thermodynamics. Hence, the isothermal must be parallel to S axis where there is no change in the temperature. And the adiabatic lines must be parallel to the T axis because during the adiabatic process there is no exchange of heat takes place. Therefore, if there is no absorption of heat or if there is no rejection of heat, then there will be no change in the entropy. Hence, the lines AD and BC are at a constant entropy, which represents there is no change in the entropy during the adiabatic process. Thus, we can say a Carnot cycle is bounded by two isothermals and two adiabatic lines, and these lines must be rectangle in a TS diagram. If we find out the area of this triangle, that area will be equal to the work done in one cycle of a Carnot's engine operation. Now, consider a Carnot reversible cycle which is plotted on a TS diagram. Suppose S1 be the entropy of the working substance in state A and S2 be the entropy in state B. Let Q1 be the heat absorbed along AB. The absorption of heat leads to isothermal expansion at a constant temperature T1, and a similar way, if T2 is the amount of heat rejected to the sink, which is shown along CD, it is a process of isothermal compression at a constant temperature T2. Now we shall calculate the change in entropy in two isothermals and two adiabatic process. We can calculate the entropy for each line or for each curve AB, BC, CD and DA. Now, in going from A to B along the isothermal expansion AB, there will be a gain in entropy of the working substance because there will be absorption of the amount of heat dQ in the process of isothermal expansion. So this change in entropy or the gain in entropy can be given by S2 minus S1 is equal to Q1 by T1, where Q1 is the heat absorbed at temperature T1. In going from B to C along the adiabatic expansion BC, there will be no absorption of heat or there will be no rejection of heat since it is adiabatic expansion. Hence, there is no change in the entropy. Since Q is equal to 0, the change in entropy is also 0. Next, in going from C to D, which is another isotherm which represents the isothermal expansion CD, there will be a rejection of heat to the sink. So as the heat decreases, there will be loss of entropy of the working substance. But in other terms, there will be gain of entropy of the sink. So now here we consider only the entropy of the working substance we are measuring, and we get the expression for that. So for the curve CD, the change in entropy S2 minus S1 is equal to Q2 by T2, where Q2 is the amount of heat which is rejected into the sink at the temperature T2. Again, dA is another adiabatic expansion without the involvement of heat, hence the change in entropy will be 0 along dA. Now we shall give the expression from the equation 1, Q1 is equal to T1 into S2 minus S1. The equation 1 is rewritten like this, and from equation 2, Q2 is equal to T2 into S2 minus S1. Therefore, if you take the difference of this amount of heats, Q1 minus Q2 is equal to T1 minus T2 into S2 minus S1. So this product will give us the calculation of the entropy. Therefore, the quantity Q1 minus Q2 represents the external work done in one cycle, and T1 minus T2 into S2 minus S1 is the area of the rectangle on the TS diagram. By finding out or calculating this area of the rectangle on the TS diagram, it represents the external work done in a reversible Carnot cycle. We can easily find out the amount of external work done in a reversible Carnot cycle by the calculation of the area of the rectangle. This is one advantage of the TS diagram. It is also very useful in calculating the entropy of the working substance. Now let us look into the concept of absolute zero and the third law of thermodynamics. The third law of thermodynamics gives us the information about the concept of absolute zero. In 1912, Nernst stated the law as: it is impossible for any procedure to lead to the isotherm T is equal to 0 in a finite number of steps. In other words, the same can be stated as: at absolute zero temperature, the entropy tends to 0 and the molecules of a substance or a system are in perfect order. This is the third law of thermodynamics. We all discussed from the kinetic theory of gases and from the thermodynamics, so that the matter will have some energy, and due to the kinetic energy of the molecules, there will be some entropy for the molecules. The entropy will be minimum in solids, and as the solid converts into a liquid or the liquid converts into gas, the disorder increases and thereby the entropy also increases. If in a reverse, if the temperature of the system or the matter is gradually reduced, the disorderness or randomness gradually decreases and the entropy decreases. If we further decrease and make the temperature of the system or the matter as absolute zero temperature, then there will be no motion of the molecules and there will be no vibration of the molecules and there is no kinetic energy of the molecules. Hence, the entropy of the system will be 0, exactly 0, and the molecules of the substance or a system will be in a perfect order. So this is the inference of the third law of thermodynamics. In physics, absolute zero is considered the lower limit for the temperature of any system, and the third law of thermodynamics can be formulated in terms of this temperature. According to third law of thermodynamics, it says that you can't reach absolute zero, that is the 0 Kelvin or the temperature minus 273.15 degrees Celsius through any process that uses a finite number of steps. It is very obvious because if we consider the perfect gas equation PV is equal to RT, so from that equation, if T becomes 0, absolute 0, then PV is equal to 0. That means P is equal to 0 or V is equal to 0. In other words, the pressure of the gas will be 0 or the volume of the gas will be 0. By doing any number of process in any number of steps, we cannot make the temperature of the system as 0, because according to third law of thermodynamics, if the temperature of the system becomes 0, then there will be no volume for the system and there will be no pressure for the system. This is not possible at all practically. Hence, third law of thermodynamics just says that you can't reach absolute zero temperature. In all heat engine, there is always loss of heat in the form of conduction, radiation and friction. Only the Carnot engine says that there will be no loss of heat and the efficiency of the heat engine will be 100%, because this is the only conceptual thing and it is not possible in a practical engine. Therefore, in heat engines, Q1 by T1, the quantity Q1 by T1 is not equal to Q2 by T2. Therefore, Q1 by T1 minus Q2 by T2, if you take this difference, it will not be equal to 0, but it is a positive quantity. The entropy of the system increases and tends to a maximum value. When the system attains the maximum value and no work can be done by the engine at this stage, with the increase in entropy, the disorder of the molecules also increases. With the decrease of entropy, the disorder decreases. Now we shall discuss about 0-point energy. According to kinetic theory, the energy of a system at absolute zero should be 0. It means the molecules of the system do not possess any motion. Since there is no kinetic energy at absolute zero, the molecules of the system do not possess any motion. But according to a modern concept, even at absolute zero, the molecules are not completely deprived of their motion and hence possess some energy. Hence, the energy of the molecules at absolute zero temperature is called 0-point energy. So these are all some discussions about the third law of thermodynamics, which gives many information about the absolute zero temperature.